Assalamualaikum warahmatullahi wabarakatuh. Good morning, all. Am I audible?
Yes, Miss.
Okay,
Yes,
thank
Miss.
you. Sorry, I'm late and I cannot attend the class on site. So this week we will have an online meeting. Yeah. So this week we enter our main topic in language theory and automata. We will discuss about finite automata. So, as what I described to you in the previous week, uh, basically in this lecture, we will learn about languages. And languages is something that can be recognized by a machine, and the machine can be modeled by using automata. So automata is an abstract machine that recognize, accept, and also generate a sentence on a particular language. And each automata is equivalent to a grammar. Last week, I also show you Chomsky hierarchical. So he divided languages into four classes. The largest one is unrestricted grammar. And then next one is context sensitive grammar, then context free grammar, and the smallest one is regular grammar. What we learn in the first mid of semester is regular grammar that can be recognized by using finite automata. So finite automata is basically the simplest automata among the four automata we have here. And the application for this can be found in string searching and also regular expression. So finite automata is a computational model with limited memory because this is the simplest computation model we have, and it is also called a finite state machine or FSM, and it is used on an application that needs pattern recognition. For example, it can be used in a compiler. The lexical part must recognize which string that represents variables, names, and so on. So, if we have some language for coding, we have variables, we have constants, we have strings, and so on. So, in the compiler, they must recognize this classification so we can model it by using finite automata. Another application of finite automata is software to design and check digital circuit, for example, for ATM machine, or lexical analyzer on a compiler in which the function is to split the input text to logical unit. Or a search engine can be modeled by using finite automata as well. So the illustration of finite automata is like this. So in finite automata, we will have an input. It is a string. So we have an input type. Each of these contain symbols. Okay, and we have a state indicator here. It represents the number of states we have. And then here we have head, which represents which symbol are we reading now. And the moving direction is always from the left to the right. So finite automata is an abstract machine that consists of finite number of states, and one of the state is an initial state, with at least one state is an accepting state. So we can have more than one accepting state, but at least one state is an accepting state. And the machine will obtain an input stream which is a sequence of symbols or alphabets, and machine will move from a state to another state based on the current state and the input symbols. So here we see we have state indicator, and we see which state we are in right now and which symbol we are reading right now. So to model a finite automata, we can use state transition diagram, or we will call it as STD. A state transition diagram is a set of labeled nodes connected with a line or edge. And a state transition diagram receives an input string and output accept or reject decision. So we have an STD and we have an input string, and we compute the input string based on the STD we have, and we will give an output that is a decision accepting or rejecting. So this is a state transition diagram example. Let's say we call it M1. So this STD has 3 states. These are states. So states are represented by nodes. We have states Q0, Q1, and Q2. We have a starting state or initial state, which is Q0. So this row indicates the starting state or initial state. And then we have accepting state or final state, which is indicated by double line circle like this. It is Q2, the accepting state. And then transition, we have transition. It is directed line represents a transition from a state to another based on the current input character read by the machine. So these are transitions. So it means we will move from Q0 to Q2 if we read a letter, or we will move from Q0 to Q1 if we read a digit. And from Q2, it will go back to itself if we read a digit or a letter. Okay, so output is accept or reject. So if we end the input reading in the accepting state, so it will result in an accept. But if we are stuck, or if we are not end in an accepting state, so it will result in a reject. So for example, here we have the same finite automata, and we want to see if we will accept or reject an input string x256. Okay, so we want to read x256. So we always start from the first symbol, and we always start from the first state, the initial state. So we are in Q0 when we read this, and from Q0 we read X. X is a letter, and from Q0, if we read a letter, we will go to Q2. So from Q0, we will go to Q2, and we read 2. And from Q2, we read 2, which is a number. And based on the finite automata, when we read Q2 and read a digit, we will go back to Q2. So we read 5 in Q2. And 5 is a digit as well, so we still go back to Q2 and we read 6, and it is a digit as well. So we end with the input reading, and we are in accepting state, so it is accepted by the machine. But what if, let's say, the input string is 256 only? If it is the case, then when we first read the symbol here, the first symbol is 2. We always start from Q0, but because 2 is a digit, then we go to Q1. And here, it doesn't say anything about reading digit or letter. So anything that we read after it cannot go to anywhere. So it will result in reject. Okay. So if we cannot end the reading of it, or if it ends in a non-accepting state, that then it will be rejected. So it is accepted and it is rejected. Okay. If you have any question, please feel free to interrupt me or raise your hand. Okay. And then the implementation based on the STD, we can implement the finite automata as a computer program. So, for example, we have the previous finite automata. We can write a program for that, like this. So we always start with in initial state. So the state is the initial state, and then we read the next symbol of input string. And while not end of string, we do this. Okay, we in the case state of here. So if we are in Q0, or if we are in Q1, or if we are in Q2. If we are in Q0 and current symbol is letter, then we go to state Q2, just like this. Sorry, I will wait. Um, Wait there. So this is the previous machine. So we can see that the start is Q0 and we read the next input string, the next symbol in the input string, and while not end of string. So as long as we haven't done with the reading the input, then if we are in Q0 and if current symbol is letter, then we move to state Q2. And then if the current symbol is digit, and then we move to state Q1. Otherwise, if we read other than these two, then we will exit error. And then, wait. And then the same with Q1. So in the Q1, because we cannot read anything, then it will always exit to error routine if it is not end of string. And then if Q2, we check if current symbol is letter, then we move to Q2, or basically we stay in Q2. And then if current symbol is digit, we update the state as Q2. And then after we read the current symbol and move based on the current state, we read the next symbol of input string. And we do this until we reach the end of the string. And if in the end the state is Q2 because it is accepting state, then we return accept, else we return reject. So if we have a finite automata, we can always write a program as well for that. Okay. But if we have a transition table, so it is another way to represent the finite automata. It is a two-dimensional table where each cell represents the summary of a transition diagram, and row index represents state and column index represents symbol. And each cell contains the next state based on the current state or row index, an input or column index, and an addition column labeled with an of string, EOS, contains accept or error. And by using transition table, a program only needs to read the transition table. Therefore, if there is any update on the automata, we only need to modify the transition table and we will have a more flexible program. And how do we transfer STD to transition table? We first insert n rows that represents the states in the STD, and then insert m columns that represents the alphabets, and add an EOS column and fill the end of string column with accept for rows that represents accepting state and error for other rows. And for other cells, fill the next state based on the alphabet and the current state. And then we fill error if there's no transition in the STD. So for example, in the previous STD, we can write this as the transition table. First, we have a row for each state, and then we have column for each possible symbol we read. Okay, but we also can, for example, letter, or for example, letter is A, B, C, D, and so on, right? You can write if I read A, if I read B, if I read C, and so on. But because until Z, but because they are the same, we can just combine it into letter and also digit for 0 to 9. Okay, so if we read letter, what will we have? If we read digit, what will we have? Here, we don't see any other symbol, so these two are enough. Plus, we need one extra column for an of string. Okay, and then from Q0, from the first state, how if we read letter? If we read letter, we will move to Q2. That's why we have Q2 here. And if we read digit, we will move to, if we read digit, we will move to Q1. That's why we have Q1 here. And if we reach n of string in Q0, then it will be error because it is not accepting state. And then for Q1, in Q1, if we read letter, we cannot go anywhere, so it is error. If we read digit from Q1, it doesn't go anywhere, so it is error as well. And if we reach n of string here, it is error as well because it is not an accepting state. And for Q2, if we read digit or letter, we will go back to Q2. And if we reach n of string here, it will be an accept. Okay, so each row, each state have their own row, and each symbol have their own column, and we add extra column for n of string. It always error for non-accepting state, and it accept for accepting state. And if we have a transition table, we will have a program like this. If state equals to Q0, we will repeat this. Read the next symbol of input string, and we just need to check the table. Current state will be the cell, the value of the cell state input. So what state we were in and which input, which symbol we reading. That is to update the state, and if state is error, then we return reject. If we occur error, then it will be reject. So even if we have different finite automata, it will still hold. Okay, even if I change this into Q1, we don't need to change the program because it just read the content of the table. But in this case, if we update, for example, here I make, or here, for example, I make letter, then I need to update this, right? But here, if we use transition table, if I update this, for example, then I don't need to update the program because it basically just read what we write in the table. Uh, Another example, we want to convert a float machine STD to a transition table, and we want to write the program pseudocode based on it. So this is a float machine, which is an automata that recognize a float. Um, and if we want to build or write the transition table, we just need to have again row for each state. So we will have Q1, Q2, Q3, Q4, Q5, Q6, and Q7. And then we also need to have column for each possible symbol. So each possible symbol is digit, and then what else? E here. Here we also have a comma, and then we also have plus and also minus. Yeah, and that's all. And again, we need an offstring, an extra column for an offstring. And here we see if we are in state Q1, if we read digit, we will go to Q2. So this is Q2. Otherwise, we don't have a way, so it will be error. And it is not an accepting state, so an offstring is error as well. For Q2, if we read digit, we will go to Q2. If we read E, we will go to Q5. If we read a comma, we will go to Q3. Otherwise, it is error. And it is not an accepting state, so it is error as well. We can go through all of the states until we finish the table. Okay. And the program will be basically the same. Here we have the initial state is Q1, and then we read the next symbol. And in case of the symbol is the possible symbols, then we update the state and so on. Here is the state. So because this is basically the same with what we have here, but because in this case we classify as digit, then in this case we just need to define. If we read 0, 1, 2, 3, and so on until 9, then we consider it as a digit. Or if we have comma, E plus minus, we consider it as a symbol, for example, and so on. But basically the other is still the same. So now you already know what finite automata is, and you already know how to make transition table from it and how to make a program from it, the pseudocode. So how we design a finite automata? So based on the reader as automaton principle, we need to think what should be memorized from the input string, finite state, finite memory. For example, given an alphabet 01, so it is, we talk about binary string, and we design a finite automata that accept binary string contains odd number of 1. What should we memorize? The number of 1 that so far has been read by the machine, and whether the number is even or odd. Because we only have two possible conditions, the number of ones we have read is either even or odd. And next we draw one state for each possible condition, and we draw transition between state. Okay, so basically, if we want to design a finite automata, the first thing we need to do is think about what should we memorize, or what should we take a note about. And for each point, make a new state, and then we draw a transition between the each between the states. So for example, here we want to design a finite automata that accept binary string contains odd number of 1. Okay, so we want the number of 1 be odd. So the number of 1 can be even or odd. So up until now, what we read until now, is it even or is it odd? So we can make two states, even and odd. And then, sorry, it's supposed to be here actually. So we can make two states, Q even, Q odd. This state means up until now, we have read even number of 1. But for the other, for this, up until now, we have read odd number of 1. Okay, so which state we are currently in, it based on what we read so far. And then from that, we can write the transition. So if we are in this state, in the sense that if we have read even number of 1, for example, here we have read this, and we read the next symbol is 0, then the number of 1 we have read, it doesn't change, right? It's still even. That's why in this state, if we read 1, if we read 0, then the number of 1 we have read is still even. But if I read 1, then the number of 1 we have read so far now becomes odd number. And if we are in odd state, in this state, the number of 1 we have read is odd. Then if we read 0, it doesn't change the condition. But if we read 1, now the number of 1 we have read is become even. Okay, so draw a state based on several conditions that may occur during the reading. And then we draw transition, how if we read this and how if we read that in each state. And next, we need to determine initial state. So initial state means we haven't read anything. So if we haven't read anything, the number of 1 we have read is 0. and it is even. That's why the initial state is in the even state. And the accepting state, here we want to accept if the number of one is odd. So of course, the odd state will be the accepting state. So we can have our finite automata here. Okay. Is there any question? Now,
That was
yeah. So now an example. So let's say we want to design a finite automata that recognize binary string contains 001 substring. So 001 substring means we will accept this because it has 001. This also have 001. This also have 001. Here we also have 001. So the first step is what should we memorize? What should we take a note of? Okay, so let's say when we manually uh, recognize or if we manually want to decide if it is accepted or not, we need to check 001 if it is there or not, right? Or let's say we check it here. We want to check 001. When we read the first one, of course, it is not a part of this. When we read the next symbol, of course, it is not part of this. And go on until we read 0. Oh, it may be the first 0 we are searching for. And we read another 0 after that. Oh, it seems like it is the next 0 we are looking for. And if we find one, oh, it is found, right? We will do something like that. So basically what we need to check is have we found the first 0? And then have we found the uh, first 0? So the second 0, or we found 0? And then have we found 001? So we will need these three. And another. We haven't found any 0. Okay, so in the case of this, like 1, we haven't found anything that related to 001. So we can have 4 states here. Let's say this is Q0, this is Q, or I can name it anything, right? So let's say this is Q0, which means we have found the first 0. This is, let's say, Q00, which means that we have found the 0. So the first 0 with the second 0 together. And for this, let's say we say Q001. So we will have 4 states. We have Q, we have Q0, we have Q00, and we have Q001. And we draw transition from the state Q, the state where we haven't found any 0. In this case, if we read 0, then we haven't found anything. Let's say, for example, like this, and we found 0. Oh, it may be the first 0 we want to find, right? So we can go to here, the state where we found the first 0. And then if we found another one, if we found one, if we read one from here, it means we haven't find anything related to 001. That's why if I read one, then we will go back to Q. And then in this state, if we have found the first zero, if we read zero, another zero, so previously we already read this, and if we read another zero, it may be this part, what we want to find, right? So we found the first zero, zero. If we read another zero, how if we read one after that? So in this case, previously we read zero, and in this case, let's say we read one, then it is not related at all to 001. So it means we go back to the first state where we haven't found any, uh, maybe not any zero, anything related to 001. So we doesn't seem uh, to have found 001 yet, or even part of it. Okay. And then in this state, we have found 0, 0. So we have found 0, 0. What if after this case, we found 1? Then of course, we have found 0, 0, 1. Then in this case, if we found read 1, oops, why is it? Wait. Oh. If we read 1, then we have found 0, 0, 1. But how if we read 0? So in this condition, we have read 0, 0. And what if we read 0? Then this 0, 0 may be what we searching for, right? We just need to find 1 to find 0, 0. That means if I found 0, I can go back here because I I still found 0, 0 there. Okay, and from 0, 0, 1, this state, we have found 0, 0, 1. So either we read 0 or 1, it doesn't change the fact that we have found 0, 0, 1. So either we read 0 or 1, it stays there. The initial state would be a state where we haven't read anything. So of course we haven't found anything. So this is the initial state. And the accepting state, in this case, we want to find 0, 0, 1. So this will be the accepting state. Okay, any question here? No, yeah.
No, miss.
Then, yeah, this is what we have. Next, odd machine. Well, it is similar to, or it is exactly the same as what we discussed in the first example. So I will not back to that. Even machine, just the, what it is, the opposite of the odd machine, right? So we have Q even and we have Q odd. And if we already found, oh, sorry. This is not a number of ones. This is represents binary that is even. So if it is even, then it will ends in 0. But here it will ends in 1, right? So in this case, then we, if a binary if a binary string represents an odd number, then it will ends in 1. If it represents even number, it will ends in 0, right? So we can have two states, either the last symbol we read is 0, or the last symbol we read is 1. If the last symbol we read is 0, then we read 1, then we will go here because the last symbol we read is 1. If we read 0, we have here. And if we are in state Q1, we read 0, then the last symbol we read then is 0. And the last symbol we read is 1 if we read 1. And the initial state will be the accepting state. We talk about accepting state first. The accepting state will be 1 because we want to accept odd machine. And initial state is if we haven't read anything, then we are not ending in 1, right? Then this will be the initial state. And for the even machine, it works similar, but just the opposite. 111 machine is a machine accepting binary string containing 111. It is similar. We uh, we will have Q, which is a state where that's saying we haven't found anything related to 111. Q1, let's say we have found 1 only. Q11 means we have found 1 1, 2 ones together. And Q111 means we have found 3 ones together. And we can draw the state. And from Q, if we read 1, then it means we have found the first one. If we read 0, we go back. From Q1, if we read 1, it means, previously we have found 1 1 and we read 1, then we found 2 ones together. If we read 0, we will go back. And this is also will be the same. And here, after we found 111, doesn't matter if we read 0 or 1, it will still be accepted. Okay. So here we have, this will be similar. Yeah, it works actually similar. This is Q. With the previous example, we can name it Q. This is where we have found Q0. This is the state where we have found Q01. This is Q010, and this is Q0101. Okay. So that is finite automata, but actually we have two different kind of finite automata. The first one is deterministic, and the second one is non-deterministic. In deterministic finite automata, each alphabet or input symbol on a state can only causes one transition to the next state, or in other words, we have no ambiguity. But in non-deterministic finite automata, each alphabet or input symbol or state can cause transition to more than next one state. So for example, if we have a state, then if we read 0, we can go back to itself, for example. But if we read 0, we can also go to another state. So this is non-deterministic automata because in this case, if we have 0, we have to two possibilities. And an example for deterministic finite automata is what we have made in the previous slides. We haven't got non-deterministic finite automata yet there. And this is, for example for non-deterministic finite automata. Here we see if we read 0 in Q0, it can go back to itself or it can go to Q1. In deterministic finite automata, an abstract machine consists of finite number of states. It is the same. One of the state is the initial state, and at least one state is an accepting state. And the machine will obtain an input stream, and the machine state will change from a state to another state based on the current state and the input symbol. So basically, this is the same what as what we learned previously, but in deterministic finite automata, we cannot have one symbols go to different state. So no ambiguous transition, and the rest is the same. In formal definition, we can write finite automata like this, deterministic finite automata like this, where Q is the set of states, sigma is state of alphabets, delta is the transition functions, and Q0 is the initial state, and F is the set of accepting states. So for example, here, this is the formal definition of STD we have here, which can be written like this as well. Actually, if we count it as a transition diagram, we need to have an of string here as well. Okay. So Q is the states, sigma is the symbols, delta is defined like this, and Q1 is the initial state, and F is a state of accepting state. Or this can also be written like this. So delta Q10 means a transition from Q1. If we read 0, then we will go to Q1. If we are in Q3 and we read 0, then the transition will go to Q2, and so on. And then in the STD of a DFI, we must have exactly one initial state, minimum one accepting state, minimal one accepting state, and from each state, there is only one edge that leaves those state for each input, and it must be fully defined, which means on each state, we must define transition for each input symbols in the alphabet. So for example, we have a float machine we saw before, and here it is not fully defined because in from Q1, it is not defined how if we read E, how if we read comma, how if we read plus or minus symbol. So it is not fully defined. Where deterministic, STD for deterministic finite automata must be fully defined. So to make it a fully defined, we need to add an additional state and basically just throw everything that is not defined there. Okay. So for example, this is the initial STD and we want to make it fully defined. We just need to add another state and we just defined oh, we just defined everything that is not defined yet. And of course, don't forget to add a transition to itself where it can read anything. Okay, so for example, here from Q1, The one that is not defined is E plus minus comma. So we will define it to the new state. And here we have no plus and minus symbol that is defined. Here we can have E plus minus comma. Here we have plus minus. From here we have E. From here we have plus, minus, and also E. And from here we have everything. Oh, and comma, sorry. I forgot about that. Okay, so we kind of throw everything that is not defined yet to the new state. And of course, we need to define a new transition to itself for every possible symbol it can read. And now it become fully defined. Okay, is there any question?
Miss,
Yes.
can I ask if you can, after this class, to upload the PPT, since in the LMS it's different
Yeah,
and
yeah.
the one that you have is more complete.
Okay. Yeah.
Thank you.
Okay. Any other question? If no, I will give you some exercise. So I will create a breakout room. You can work in group of 2 and do the exercise. The answer must be handwritten. You can rewrite the, I will show you the, wait. I will show you the example of the exercise I will give you. Oh, wait, before that, let us do the attendance list first. Please prepare your MyTelu app. While I'll send the slides to the group for now, but I will upload it later in the LMS.
I'm sorry, Miss.
Yeah,
For the presency, I can use my Telu apps because I have my new device, so I'm not downloaded yet.
okay, no worries. We will do it manually as well. So
Thank
Amira
you.
are you there? Amira, Ahmad Faiz, Muhammad Zayed, Calvin, Nesha, Razaka, Muhammad Rafi,
Present,
Razaka
Miss.
hadir, Miss.
Rafi here,
Raffi.
Present, Miss.
and Razaka here.
Razaka.
Okay. And then Almet, Muhammad Raka.
Present, Miss.
Okay. Lale is here. Fadlur Rahman, Handy, Revi, Fatur Rahman, and Rizky.
Present, Miss.
Okay. And then Fayaza.
Present, Miss.
Okay. So not here are Fatur Rahman, Repi, Fadlur Rahman, Almer.
Miss,
Yes.
Calvin Nathaniel, I can scan the barcode.
Okay. Almer, Nesha, Calvin,
Mira tuh, Miss.
Zayat not here, Ahmad Fai is not here, Amira is here. Okay. So, wait. So your exercise will be something like this. You will need to draw a state transition diagram and also write the transition table for it, but it must be deterministic finite automata. Okay. And it is for example, for binary string that starts with 00. You can write directly here. You can print first and then write it, or you can use any applications in your device to write it here, or you can just rewrite the problem in a paper and you answer it there and you take a picture of it. Okay, it can be done in a group of 2. I will divide you into breakout room. So I will provide a breakout room you can enter, but the each problem can only be done by 2 people. I will, yeah, okay. I will create 20 breakout room. There are 20 type of questions, though. So do the number of question that is the same as your number of breakout room number. For the question, I will give the link to you in the chat room. Wait.
Miss, can I ask something?
Yes.
Can I use my iPad to write it, or I need to
Yes.
paper?
No, you can use your iPad.
Thank you.
You can check the link I sent you in the chat group. Wait, and I will stop the recording first.